Hola, mis estudiantes. Yo busco un libro en español. Se llama Pobre Ana. Y yo voy a leer. Ana es una chica con problemas. Okay. Oh, we're over 20. So I'm going to get started. Okay, good morning, class. Hope you guys are doing well. Okay, so for the last two lessons, we've talked about circular motion. And if you've been noticing the titles of the quizzes, they were called circular motion and gravitation quizzes. And so now we're going to talk about gravitation a little bit. So why does gravity go together with circular motion? It's because gravity causes things to go in orbits, which is a form of circular motion. So that's why they kind of go together. Okay. So I want to talk really briefly about the weight force. The weight force we already know about. The weight force is the force due to gravity. Okay, and its value is m times g. Okay, where m is the mass of the thing that is experiencing the gravitational force, and g is the acceleration due to gravity. Okay. All right. So on Earth, the acceleration due to gravity was 10. Roughly, it's 9.8 meters per second squared. If you go to other planets, they have different accelerations due to gravity. All right. So what we're going to do is we're going to talk about that again, but what we're going to do is call the acceleration due to gravity by a different name. Okay. So there's something called the gravitational field. Okay, which is the exact same thing as the acceleration due to gravity. So it is another word. It's simply another word for the acceleration due to gravity. Okay, it's another word for the acceleration due to gravity. So we can say the force due to gravity is equal to mg, where g is, so again, these are synonymous. The acceleration due to gravity is the exact same thing as the gravitational field. It's just that the AP exam uses this term gravitational field, okay? When I took physics, we always just called it acceleration due to gravity, but the AP Physics 1 exam could call it acceleration due to gravity or gravitational field. So you need to be prepared for that. So this is the gravitational field experienced by the thing. Okay, and m is the mass of the thing in the gravitational field. Okay, now generally speaking, the units of acceleration due to gravity, well, because it's an acceleration, they were meters per second squared. So we said Earth has an acceleration due to gravity of 9.8 meters per second squared. But when we're talking about gravitational fields, we use an equivalent unit, okay? And that unit is obtained by taking this equation and dividing both sides by mass. And we see that gravitational field is force per mass. So force is measured in newtons and mass is measured in kilograms. So an equivalent unit is newtons per kilogram. And this is the preferred unit when we're talking about gravitational fields. Okay? It's completely okay. It's completely valid if you say meters per second squared, but it's just preferred to use newtons per kilogram. So you can say the gravitational field of the Earth at the surface of the Earth is 9.8 newtons per kilogram, or you could say the acceleration due to gravity is 9.8 meters per second squared. It's the same thing, all right? It's just a little quirk in the way we talk about certain things in physics, okay? So that is the gravitational field. So the main question that we want to answer today is, how can you calculate the gravitational field? Okay, so we're going to learn an equation for calculating the gravitational field. All right. And so basically, excuse me, there's a couple of things that the gravitational field depends on, okay? The gravitational field depends on how far away you are. So the further you move away from the Earth, the less of a gravitational field the Earth creates in your vicinity, okay? So if you're, 10 light years away from the Earth, the gravitational field that the Earth creates 10 light years away from it is tiny, so you won't really feel that gravitational field, okay? So it depends on how far away you are from the thing that is creating the gravitational field. And it also depends on the mass of the thing creating the field. Okay? All right. So the more massive the thing is that's creating the gravitational field, the stronger that gravitational field is going to be. So, for example, if we're in the Earth's gravitational field right now, so the mass is the mass of the Earth. If you are, if you're in the sun's atmosphere, the mass would be the mass of the sun. Okay, so there's a certain, the more mass you have, the stronger the gravitational field is going to be. So if you wanted to experience the greatest possible gravitational field, you would go as close as possible to a really massive object. So this is why things like black holes have the largest gravitational fields, because they're extremely massive and they're very small, so you can get really close to them. Okay. So Isaac Newton, in addition to coming up with his laws of motion, also figured out the formula for gravity. Okay. And this formula is still used today for calculations by NASA. It's a really useful formula. Okay, so it's called Newton's law of universal gravitation. Okay, and so I want to just draw a little picture. So let's suppose you have something like a planet, okay, and here's an astronaut or something, okay. So we are going to define big R. Oh my god. To be the distance from the astronaut, between the astronaut and the center of the planet. So this is an important point. Big R is the distance between the thing and the center of the planet. Not the surface, but the center. Okay. All right, so that is called R. And I'm going to use a big M to be the mass of the thing that is creating the gravitational field. So this is the mass of the thing creating the gravitational field. So I use the Majin M from Dragon Ball for that. I don't know why, just to differentiate it from the mass of the thing experiencing the gravitational field. Okay. So the planet is creating the gravitational field, so it is the Majin M from Dragon Ball, and the astronaut is the thing experiencing the gravitational field, which is little m. Okay. So the law of universal gravitations gives us a formula for the gravitational field. And it says that the formula is big G times big M divided by R squared. Okay. So we can see that it actually encapsulates these two statements here. So we can see that if you get further away from the planet, the R value increases. And R is in the denominator here. So the bigger the R value is, the smaller the gravitational field. So that's exactly what we said, okay? The further you are away, the weaker the gravitational field is. We can see that Majin M is the mass of the thing creating the gravitational field, okay? And we can see that it's on the numerator, so the bigger the mass of the thing, the stronger the gravitational field, okay? So it's exactly what we said. Now, keep in mind that the gravitational field is the acceleration due to gravity, and acceleration has a direction. So what is the direction of G? Is towards the center. Okay, so this astronaut is going to accelerate towards the center of the planet. If the astronaut was over here, they would accelerate towards the center. If the astronaut was right here, they would accelerate towards the center. Now you might notice that I've drawn these three arrows as different sizes. Okay? And the reason I've done that is excuse me. The reason I've done that is this point right here is farthest away from the center of the planet. So it's going to have the smallest gravitational field. This arrow is slightly longer because it's closer to the center of the planet. And this one is the longest because it's closest to the center of the planet. So its size changes depending on how close you are, and its direction changes depending on where you are relative to the center. Okay? Now, big G is a constant of nature. It's called the Universal Gravitation constant. And it's the same. No matter which problem we're solving, it's always going to be the same number because it's a universal gravitation constant. Okay? And its value, by the way, big G is not the same thing as little g. It's case sensitive. Okay, little g refers to the gravitational field. Big G refers to the universal gravitation constant. So big G is 6.7 times 10 to the negative 11, and it has weird units. You don't need to worry about the units so much. Newton meters squared per kilogram squared. Okay, so this stuff is our key information for today. All right. So one thing I wanted to talk about is why is it called the law of universal gravitation? Okay. So you might have heard the story of Newton and the apple, which I don't know if it's a true story or not, but the idea is an apple fell out of a tree and hit Newton on the head, okay? And that made Newton have the idea that the same force that pulls an apple towards the Earth is the force that makes the moon orbit the Earth, okay? So Newton sort of made the generalization that it's the same force that's holding us to the Earth that is holding the planets to the sun, that is holding everything together, okay? So he made that great generalization, okay? And furthermore, what Newton said is that everything that has mass creates a gravitational field. So you might notice that big M is the mass of the thing creating the gravitational field. And little m is the mass of the thing experiencing the gravitational field. But really, that's just a matter of perspective. Everything with mass creates a gravitational field. You create a gravitational field, okay? You create a gravitational field around you. The moon creates a gravitational field. The Earth creates a gravitational field. All the planets and all of their moons each creates a gravitational field, okay? All right? So it's simply a matter of perspective what we consider to be big M and what we consider to be little m, okay? If we wanted to know what is the gravitational field that the Earth experiences due to the sun, then big M is going to be the mass of the sun and little m is going to be the mass of the Earth, okay? If we wanted to calculate what is the mass that the what is the gravitational field that the sun experiences due to the galaxy, then big M would be the mass of the galaxy and little m would be the mass of the sun. Okay? So what we consider to be big M and what we consider to be little m is a matter of perspective. Okay? Furthermore, big M doesn't even necessarily have to be larger in size than little m. Okay? We could calculate the mass of the gravitational field of a baseball that is experienced by an asteroid. In which case, the thing experiencing the gravitational field would be little m, that's the asteroid, and big M would be the mass of the baseball, the thing creating the gravitational field. So it's a matter of perspective. So, as I said, you are creating a gravitational field right now, okay? Because you have mass. Everything that has mass creates a gravitational field. Why don't we notice your gravitational field? The reason has to do with big G. Big G is 6.7 times 10 to the negative 11. That means that we move this if we wanted to not write this in scientific notation, we would have to move this decimal point over 11 places. So this is a really, really small number. Okay? And so because this is such a small number, to get a gravitational field that we actually notice, the mass needs to be huge. So that's why we notice the gravitational field of things like planets and stars, but we don't really notice the gravitational field due to each other, okay? Things like asteroids, they have a large mass, but even asteroids are not big enough to create a significant gravitational field. We landed on an asteroid one time, and the landing was botched, and the lander actually bounced off the surface of the asteroid, and the bounce, because gravity from the asteroid was so weak, the bounce took like 5 days. So can you imagine if you jumped off the surface of an asteroid, your jump would last like several days before you came back to the surface because the gravitational field is so weak. So I always like to tell this joke every year, so I'll tell you guys as well. Let's say you're on a date, all right? And you're sitting across from the person. And then you say to them, "Can you feel the force of attraction between us?" And you would be correct in saying that, right? Because you have a mass. You're creating a gravitational field that is pulling the other person towards you. So there is a force of attraction between you and the person you're on a date with, okay? And if they say, "No, I don't feel the force of attraction," what can you do if you want to make them feel the force of attraction? Well, you could simply, instead of sitting across from them, you could move around and sit next to them, move closer. And then you say, "How about now? Now do you feel the force of attraction?" And that would actually increase the force of attraction. Why? Because you have, by moving from sitting across from the person to sitting next to them, you have reduced the R value, the distance between your centers, which increases the strength of the gravitational field. All right? So if someone says they're not attracted to you, you move closer and they're a little bit more attracted to you. All right? This is, of course, a joke. If someone says they're not attracted to you, then you should not move closer to them. But in the physics sense, it is true that if you move closer, they're more attracted to you. All right. So The other thing that I wanted to talk about is density, because the AP exam does have density on it, so I just want to review density. So density is typically denoted in physics by the Greek letter rho, R-H-O, kind of looks like a P. And density is mass divided by volume, okay? Units of density are kilograms per cubic meter. All right, kilograms per cubic meter. So we are going to use this today. So I think I'm just going to do one example today, but we're going to use this today to calculate the mass of a planet. So what if you knew that a planet is made out of rock of a certain density? Because rock has a certain characteristic density. So then you could multiply both sides by volume, and you could get the mass. Okay. Since we're dealing with things like planets, the volume is going to be the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. Okay, so that is the mass. All right, so we're going to do an example that just kind of puts all this together. Okay, so consider a planet made out of rock of density let's say 6,000 kilograms per cubic meter, and radius, let's say 4.4 times 10 to the 6th meters. So we have to use scientific notation when we're doing gravity problems because the numbers are astronomical, okay? By the way, the Earth has a radius of 6 times 10 to the 6th meters. Okay, calculate the gravitational force on a, let's say, 90 kilogram satellite that is 2 times 10 to the 6th meters above the surface. So the satellite is not on the surface. The satellite is above the surface. All right, so we're going to do this problem in steps. So the first step is going to be to get the mass of the planet. For some of the problems in your quiz today, I just give you the mass of the planet. I just say I say the mass of the planet is. But for a few of them, I give you the density and I have you calculate the mass of the planet. Okay? So getting the mass of the planet, we're going to use density times volume. Planets are spherical. Okay? So we get 6,000 times 4/3 pi times 4.4 times 10 to the 6th cubed. So let me calculate that. It's so this mass, so the mass of the planet, so that's big M because the planet is the thing creating the gravitational field, is 2.1 times 10 to the 24th kilograms. I do want to talk a little bit about putting scientific notation numbers into the calculator, okay? Let's say you wanted to do 4.4 times 10 to the 6th cubed. Some of you might type something like this into the calculator. You might type 4.4 times 10 to the 6th cubed. No. That is not good. Okay? That is not good. What you want to do whenever you raise a scientific notation number to a power is you want to put that entire scientific notation number in parentheses. Okay? So I put this scientific notation number in parentheses, and then I cube that. All right? So this is the correct way. I'm trying to save you guys some time on the homework, because believe me, if you cannot type scientific notation numbers into your calculator, you might. This homework assignment is super simple. The most difficult thing about it is plugging things into the calculator. Okay. So if you have troubles plugging things into the calculator in scientific notation, then come see me during office hours. Okay, so now we have to calculate the gravitational field at the location, or I should say, calculate the gravitational field due to the planet at the location of the satellite. Okay? So, we're going to use our formula. Little g equals big G times big M over R squared. Okay? Now, we have to plug in numbers now. So big G is 6.7 times 10 to the negative 11. Big M is from right here. This is the mass of the planet. 2.1 times 10 to the 24th. Okay? And then we have to divide by a number. Now keep in mind, we got to be careful here. All right? The reason we have to be careful is this R in this equation represents the distance between the centers of the object. So, if this is a planet and the radius of the planet is, say, R1, and you're a distance R2 above the surface of the planet, then the R value you use in Newton's law of universal gravitation is going to be R1 plus R2. Because if you're out here, then your distance from the center is the sum of these two distances. Okay? So if we look at it, the way I wrote this problem, the planet has a radius of 4.4 times 10 to the 6th, and then you're that far above the surface, so your distance from the center is going to be the sum of those two numbers. Okay? So R, big R, is going to equal 4.4 times 10 to the 6th plus 2 times 10 to the 6th, which is, of course, 6.4 times 10 to the 6th. Okay? So when you, so notice how we have a ratio of scientific notation numbers. I want you to calculate the numerator first and then the denominator first. Okay? So let me calculate the numerator. 6.7 times 10 to the negative 11 times 2.1 times 10 to the 24th. So the numerator is 1.4 times 10 to the 14th. The denominator, again, I'm putting like this. I'm putting the entire 6.4 times 10 to the 6th in parentheses and then squaring it. So I'm going to type in 6.4 times 10 to the 6th squared, like that, okay? And I get 4.1 times 10 to the 13th. Okay, so here we've got to be careful, all right? So how do we divide scientific notation numbers? So let me tell you how to not put it into the calculator. Some of you might be tempted to do something like this. 1.4 times 10 to the 14th divided by 4.1 times 10 to the 13th. This will give you the wrong answer. No. You need to put the entire numerator in parentheses and the entire denominator in parentheses and divide those, okay? So what you should type in is parentheses 1.4 times 10 to the 14th. So I've got the entire numerator in parentheses divided by, and then the entire denominator in parentheses. 4.1 times 10 to the 13th, like that. So that's what I'm going to type into my calculator. All right? Trust me, do it this way and you won't get the problem wrong. Your calculator can give you the wrong answer if you don't know how to use it. I'm teaching you how to use it. And we get that the gravitational field is 3.4 newtons per kilogram. All right? So we got the mass. Now, from that mass, we have the gravitational field. And now what we do is we calculate the gravitational force. The satellite experiences. Okay, and so that comes from the very first equation. It comes from this equation. The force of gravity is the mass of the thing in the gravitational field times the size of the gravitational field experienced by the thing. So force due to gravity is mass of the thing times the size of the gravitational field it experiences. The satellite is a 90 kilogram satellite. We calculated that it experiences a gravitational field of 3.4 newtons per kilogram. And so multiplying those out, we get a gravitational force of 307 newtons. Okay? So basically what I've done, this example is the most difficult of the homework problems I gave you today. So hopefully you can get through that one quite easily. All right. That's my lesson for today, and I'll see you in the